Problem number 70. If V1 and V2 are four-dimensional subspaces of six-dimensional vector space V, then the smallest possible dimensions of V1 intersection V2 is. We do not have any options. So problem says our vector is six-dimensional vector space where V1 is four-dimensional subspace and V2 is four-dimensional subspace. Our vector space is six-dimensional given, and V1 is four-dimensional means it has only four vectors, not r power 4. As in basis, if we have only two vectors of dimension 4, a1, a2, a3, a4 and likewise, then let us take a vector space which has a1, a2, a3 and a4 as dimensions, and vector b as b1, b2, b3, b4. Let us increase dimension in vectors. It will be a5, it will be a6, b5 and b6. Now our vector has dimension 6, then it will become r power 6. In this space our vector has dimension 6, means it has r power 6, or we can say six-dimensional vector space. Six-dimensional vector space. In that six-dimensional vector space, it is a subspace. This is a subspace, and this is called vector space. This is called vector space, and these are the vectors in a space. Now if we have six independent vectors, we call it as basis for the space of r power 6. Now in this problem, it has only two vectors, which means it is a subspace of six-dimensional vector space. Here in this problem, V1 and V2 are four-dimensional subspaces. Then V1 equals let us take vector as first, second, third, and last will be fourth vector. So this becomes our 4-dimensional and with 4 vectors. This is 4-dimensional vector, but dimension of this particular vector is r power 6. And our v2 will be first vector, second vector, third, and this will be last vector. First, second, third, and 4 vector we have. So it becomes 4-dimensional and with 4 vectors. Now we have dimension of first vector as 4 and dimension of v2 is equal to 4. Then smallest possible, then smallest possible dimension of v1 intersection v2 is, we will find out. Now our vector space is 6-dimensional vector space. Then our basis must contain 6 linearly independent vectors of dimension 6. Even though v1 and v2 are subspaces, but the basis must contain 6 independent vectors of dimension 6 and basis in union of v1 and v2. So we can write dimension of v1 union v2 is equal to 6 as vector space is of 6-dimensional vector space. Therefore basis contains maximum 6, not more, not less, exactly 6 linearly independent vectors in our basis. That's why we can write dimension of v1 union v2 is equal to 6. Using formula from set theory, which will be dimension of v1 union v2 will be equal to dimension of v1 plus dimension of v2 minus dimension of v1 intersection v2. So it will become 6, then which will be equal to 4 plus 4. v1 is 4, v2 is 4 minus dimension of v1 intersection v2 which is required. So finally we get dimension of v1 intersection v2 which is equal to 8 minus 6 which is equal to 2. So answer will become dimension of v1 intersection v2 is equal to 2. Now this 2 signifies that in v1 and v2 two vectors are common. So in v1 and v2 we have two vectors in common, like we have here v1 and v2. So any two vectors might be common.